Hey everybody, Justin here from Statistical.com, and I wanted to use this video to talk about a book called Bernoulli's Fallacy: Statistical, Illogic, and the Crisis of Modern Science by Clayton, and to do my book review about it. And just to give some background, I have a bachelor's in math, a master's in statistics, and I've been a mathematical statistician for the last 17 years. Um, so this is the book, Bernoulli's Fallacy. And I'll provide links to every book, Amazon links to every book that I talk about here. Um, while I didn't agree with the contents of the book, I think it's a pretty thought-provoking and well-written book, so I would suggest checking it out. But yeah, let me get on with the review. So this book is essentially about what Clayton calls Bernoulli's fallacy. So it kind of relies on the transposed conditional, saying like, if D's are data and H is a hypothesis, then kind of confusing the probability of data given the hypothesis with the probability of hypothesis given the data, or using only sampling probabilities could be called Bernoulli's fallacy. I would actually call Bernoulli's fallacy just what Clayton's vision of frequentist statistics is, personally. Um, so any of those things could be, Bernoulli's fallacy. So Clayton gives some history, and just to give my understanding of the history, you know, since a long time ago, Cardano and others noticed that if you get more and more observations of something, the more accurate your estimates seem to get, on average, of course. There's variation. Bernoulli, in the early 1700s, derived what called the weak law of large numbers, and I just used WLLN to denote that. And that explains that idea mathematically. And over time, that was made more mathematically rigorous, kind of less restrictive settings, stronger convergence, and that gives us the strong law of large numbers. I have a diagram here, and I'll make it a little bigger just to show the, well, actually, I won't make it a little bigger. That was too big. To show the basic idea, this is just informal, If we have this horizontal axis be the number of coin flips, and the vertical axis, we're just keeping track of the frequency of heads that we get. Now I have a horizontal line here at 50%. It doesn't have to be there. It could be anywhere. It could be at 0.35 or whatever. It doesn't really matter. But the point is that over time, over trials, and again, assuming we're flipping in a sound manner and so forth, things will start to settle down a little bit. There may be blips like around trial 1,000, it seems like that relative frequency is, much below. But over time, those deviations get less and less from that horizontal line, again, on average. Until by the time you're at around here, I just kind of stop at 7,000. It's, pretty much 0.5, So that, again, that's a highly simplified version of the strong law of large numbers, but that's kind of what's going on. So there is some logic there. The law of large numbers is not just this kind of general idea. It's this mathematical theorem that also has an empirical basis. So there's some logic behind it. Okay. Now, Venn, from John Venn, kind of Venn diagram fame, he himself discussed that the weak law of large numbers doesn't really apply to all real life events. It's not it can't apply to like everything. So he came up with these events where the weak law doesn't really come into play. Now, von Mises, okay, he wrote that, he also wrote that it's a purely arithmetic theorem, really. And again, some sequences of data don't apply. That's why von Mises came up with, talking about where place selection is or isn't relevant. If you can enter this kind of stream of trials at any point and it converges, then we can, and the relative frequency converges, then we can probably talk about probability. But if where that relative frequency ends up depends on where you enter the sequence of trials, then it's probably not probability. For example, I'm looking at my fence out there, and there's like, it's like this high, and then maybe every, I don't know, 10 or 15 feet, there's a post. And then it goes back down, and then another 15 feet, there's a post. So if you're gonna measure the height of that fence, obviously the place selection where you do that is relevant, right? So for the coin flips, no matter where you enter that sequence, if you keep flipping, it's going to converge, is the idea. Okay. So now I agree with Aubrey that, probably us frequentists believe a convergence theorem, convergence is important and underpins a part of statistics in some way, but I do disagree that they're fundamentally flawed for analyzing probability statistics. So he points out that if the x's are from a Cauchy distribution, then the weak law of large numbers fails to converge, and that's correct. But from that, I don't think you can make the leap to saying that it's flawed or frequentism is flawed or it's bad for science. These law of large numbers, they require like the mean to be finite. There's also usually some conditions on the variance, and in most real life situations, the IID is a decent approximation anyway. And in real life, means tend to be finite, and moreover, you would never know in real life the true underlying distribution. Neither I nor Clayton would know that, oh, this is a Cauchy distribution in real life, right? So I think it's a mathematically true statement that the weak law of large numbers fails to converge, but that's not the same thing as saying it's like totally flawed or whatever he's implying or stating. So I have like a little sidetrack here. Frank Harrell, who by the way is a statistics OG, and I probably agree with him like 97% on things. It kind of reminded me of an argument he had on Twitter that, or on his webpage, I forget, that frequentism relies on the central limit theorem. First of all, there's a Bayesian central limit theorem too, so it's not. I think it's very weak criticism. But Harrell's point was that, the sampling distribution of means, it takes a long time to converge if it's log normal, and so therefore frequentism's flawed or something. But if there was a log normal population, you'd see skew and you transform it, maybe take a log of it. Okay. And he says, pretty much a critic could then say, well, you don't know what transformation to take. But then how would the critic know in the first place that it's log normal to begin with? Just like Clayton cannot know a population is exactly Cauchy or whatever, however you pronounce it. So, I find a weak criticism to say like, well, for this specific pathological distribution, it fails. So therefore, it's all should be put in the garbage. I don't think that really holds water. So I have a little information here on the central limit theorem and that. But basically, Bayesians are able to know an underlying distribution exactly, right? But frequentists aren't, right? It makes no sense, okay? There's also like a critique of null hypothesis significance testing that says, assume a male took a test for ovarian cancer with specificity of 99.99%, and our null hypothesis is no cancer present versus cancer present. And the p-value happens to be 0.0001, and a frequentist would say, haha, the male has ovarian cancer, right? I find these now Clayton didn't say that, by the way. That was one I found somewhere, but we don't even need statistics for this question. You would find out in an audit that the person was male, as well as any other questionable research practices. And why this is like damning for frequentism, I don't understand. Like, why are the frequentists prevented from knowing the person was male, but the Bayesians are allowed to know that? Or why is it a problem with frequentism and not a problem with the medical test or something? You could do the exact same kind of cute little example, and instead of a p-value, substitute Bayes factors or substitute posterior probability there. It would still be the same criticism. So It's not specific to frequentism at all just because you're doing a hypothesis test. Clayton mentions Markov chain Monte Carlo and Stan at the end of the book. Now, for any, I would say, interesting or practical, maybe real Bayesian analysis, you need Markov chain Monte Carlo to solve things. And it just has a frequentist feeling about it. You're using a burn-in period. So that's like making coin flips greater than some number, because the relative frequency, again, is rough for a small number of flips. If we go up here to this graph, for flips around, I don't know, less than 1500 in this simulation, it's very rough. It hasn't settled down yet. So that's kind of like the burn-in period of a Markov chain Monte Carlo. Same thing, using more iterations. It'll have a better chance of convergence if you only do 100, 1,000, or if you only do like 100 trials versus if you do 10,000 trials, right? Using more chains, this is like flipping more coins, so flipping different coins, right? So if you have one line converging, that's some evidence, but if you have multiple lines that they all converge to the same thing, that's more evidence, right? And then starting with a different seed. If it's still converging with the different seeds, that's like entering a collective, as maybe the statisticians of the past would call it, randomly, and still getting the same relative frequency. So that's kind of like von Mises's place selection. Okay. Now in the paper, The Interplay of Bayesian and Frequentist Statistics by Bayari and Berger, they say, any Markov chain Monte Carlo method relies fundamentally on frequentist reasoning to do the computation. It generates a sequence of simulated values of theta of an unknown quantity, an unfixed quantity, theta, and then relies upon a law of large numbers, or ergodic theorem, which are both frequentist. Okay, and then it also says the diagnostics for Markov chain Monte Carlo convergence are almost universally based on frequentist tools. So your Bayesian analysis is basically, kind of underlying it is based on frequentist tools. So the idea that the law of large numbers stuff can be fundamentally flawed just doesn't hold water. Now, Clayton mentions a lot in the book examples using Bayes' theorem to critique frequentism. But this to me is a very weak criticism, because the simple Bayes' theorem, despite the name, is not inherently Bayesian as it's being portrayed. It's just a result of the multiplication rule and conditional probability. I have the equation here. Probability of A given B equals probability of B given A times probability of A, all divided by the probability of B. Now here A and B are general events. Where it becomes, I would say, Bayesian is where the probability of A is a probability distribution for a parameter, otherwise known as a prior, right? And it's definitely Bayesian where the prior is based not on maybe past experimental data, something more objective, but on just complete subjectivity. So I don't think appealing to Bayes' theorem in general for simple events is, you're basically appealing to frequentism. So he has some courtroom examples. They're interesting. I think they're actually extremely interesting. But I think they're non-conclusive, because you're assuming what are called the Bayesian calculations are correct. We just simply don't know. And even what you call the Bayesian calculations in there, they're just using Bayes' theorem on simple events. So, for example, look at the Clark case. It's kind of portrayed like it's due to frequentism or due to the transpose conditional fallacy. But the issues were that Meadows' calculation was based on assumptions of independence of two SIDS death in the same family. Also, he ignored factors such as both the babies were boys, which make SIDS more likely, and there was very questionable post-mortem examinations of the children, which could have shed evidence on the assessment of guilt or not, whatever. And there were other issues too. So I think just blaming all of that on frequentism is just, it's just not accurate. There's nothing really involved with that has to do more with the transpose conditional fallacy than other things. I mean, how does a questionable post-mortem examination have to do with a transpose conditional or frequentism? So, and more importantly, in a courtroom, you need more than logic and probabilities. You need actual evidence. So I don't find that critique to hold water either. Now, there's a book called Confidence, Likelihood, Probability, Statistical Inference with Confidence Distributions. Okay, this is a great book. Um, Talks about confidence distributions, which is like updating Fisher's notion of fiducial probability. So they talk about aleatory probabilities and epistemological probability from a frequentist point of view. They talk about updating the likelihood instead of updating a prior, and many, many, many other things that I refer to a lot in um, when I respond to critiques of frequentism. So check that book. It's really, really good book. Now, Clayton mentions Jaynes a lot. Okay, so I just wanted to read some of these because I think the bluster and the kind of puffery is hilarious. You know, um, Clayton refers to a frequentist jihad. He refers to, I don't know, wanting to start a war or end the war. I don't know, something like that. But he continues Jaynes' attacking style of like, frequentist is ad hoc, cookbook, orthodoxian, not from first principles, psychosemantic trap, loose amalgam, half-baked, repackaged, ruinous, a disease, boring, dangerously misleading, destructive, irredeemably wrong, logically bankrupt, controversial, hallucinations, broken, held together by naming, catchy slogans, folk superstition, and so forth. So, which again is hilarious since we all use a central limit theorem. We all use histograms, which are frequencies. We all use probability distributions, which are arguably the limit of frequencies. And that stuff kind of makes your, Markov chain Monte Carlo work. So it cannot be uh, a disease or something. It just doesn't make sense. But so my thing is like, well, if that's the case, why is the style of probability and stats is it the orthodox and most used in the world? Not just science, but other fields too. Um, why isn't Bayes that? Okay, if it has, I call it the secret sauce. If it has a secret sauce to solve real world problems, just you don't need to attack frequentism. You just need to do it, and just do it. Cox theorems, which are mentioned in the book, and as Cox wrote them, and Jaynes repeated, and Clayton's repeated, they're found later to not be rigorous, and they had a flaw in which Hailperin and others found a counterexample. So I have a kind of paper there. Clayton, tried to patch them up or whatever. So, I mean that you can that you can have theorems that would, other than the Kolmogorov one, doesn't really mean that the Kolmogorov ones or general frequentism again is flawed. But the Cox theorems themselves had some issues. I don't know if they still do, but now Jaynes himself wrote, Fisher was never able to exhibit a specific problem which his methods gave a satisfactory result and Jeffrey's methods did not. And I think that's false because Fisher, he was involved with very original mathematics for test of significance and confidence interval for observations on a sphere. And he solved, of the many things Fisher did, he solved the statistics questions. And those ideas moved us away from static, elastic Earth of Jeffreys to a dynamic convecting planet. And I have the paper there to show that. So that right there is an example. But I think just Fisher influencing generations of statisticians with experimental design, analysis of variance, all of his genetics work, the modern synthesis and all that. I think that's more than enough that Fisher's methods were, I don't know, are or were or whatever, more satisfactory results. And I have here that if Jaynes wants frequentists to write freak x instead of probability of x, then Bayesian should write belief of x instead of probability of x. Or probability of x given beliefs or something of that nature. Chance of x, uncertainty of x. Okay, so in the book and in other writings, Clayton really stresses that, you know, Galton, Carl Pearson, Fisher, they had eugenics interests, okay, and linking them to the Nazis and so forth. But again, um, if he wants to talk transpose conditional, I would ask him, does probability of eugenic interest given you're a Nazi imply high probability that you're a Nazi given you have eugenic interests? I mean, you could make the same argument about Bayes. You could say he was religious, and you know, if you can show that the posterior that God exists is large, okay, are all believers that were motivated like by that belief, or all believers that they have that belief that God exists, and then they commit some atrocities in the name of religion, right? Like wiping out another religion. Is that Bayes' probability fault? I don't find that I don't find that to hold water. Um, Now, one thing here. Okay, so I have some. I just talk a little bit about Bayes' theorem as a way to provide proof for the existence of God, the one they believed in anyway, and also trying to refute Hume on miracles. Um, Clayton doesn't give the full quote from Fisher about this area. Okay, so I have an article by Bodmer Sen and some other people that of Fisher's full quote, and then the article goes on to say, you know, these statements have been interpreted by some as suggesting that Fisher referred to elimination in the sense of killing, or at least compulsory sterilization or institutionalization, and so was a Nazi sympathizer. They go on to say, this is, however, in obvious disagreement with his very clearly stated views that sterilization should be voluntary, and consistent with his support for the Brock report. So I would say, Fisher was a genetics sympathizer, not a Nazi sympathizer. Um, but I think this is like, I don't know, I would almost call it probability ganda, like propaganda, probability ganda. That even if Fisher or Pearson were Hitler himself, it wouldn't change really anything about the mathematics involved, okay? Um, and analyzing a now socially bad thing using statistical methods doesn't mean that the statistical methods are flawed or should be avoided. It doesn't make sense. I mean, if there's something that's ever societally wrong to study and they use Bayes factors to study it, does that therefore mean we don't use Bayes factors? Of course not. And I say it goes double when you purposefully, or I don't know, I want to say purposefully, but when you leave out the good things that were analyzed by said statistical methods. Fisher did experimental agricultural research to save millions from starvation through crop breeding programs. Neiman was a human rights activist. Let's not mention those things, okay? Now he talks a little bit about objectivity, subjectivity. Now, subjectivity in general isn't any problem. It's really not. All scientific disciplines use subject matter, input, hunches, um, current scientific knowledge, and so on. But people really want to conflate, Bayesians really want to conflate priors, like mathematical probability distributions, with all types of background knowledge or belief. And they're not the same thing. They're not necessarily the same thing. For example, in this article by Kubiak and Kowalek, I think that's how you pronounce it, um, shows that in the loose sense of background knowledge are used in frequentism. And I put kind of in parentheses any other area of study, I would imagine. And then again, in this confidence, likelihood, and probability book, they mention instead of updating the prior or posterior distribution, updating can be done on the likelihood itself. But I think, using comparing a mathematical probability distribution on a parameter to, oh, that's the same as any type of knowledge is not true at all. I don't think those are the same thing. And I would say too, I have one of these. This is a Galton board or quincunx. Quincunx is like the design of like the number 5 on a die, just that pattern. And if we tip this over, it's just some ball bearings. Kind of like a binomial distribution that, you're getting a bell curve, right? There we go. Or us flipping the coin and watching it converge to whatever horizontal line it converges to. Or if we could theoretically, do the similar study and measure something and try to have the same or similar experimental conditions, we would see things, in general converge too. That's what I would say would be more on the objective side of things. I would also say that, your likelihoods and your data, they dominate about any priors in belief as n increases. So your beliefs, you have whatever beliefs and they're important, but is it probability? Not so sure. If more data wipes it out, then it's not really important in a sense, even though it's more observed as you have less data, because your prior would dominate more. But as n increases, your beliefs get washed out, right? So I would say that clearly some objectivity exists with probability with science. I mean, what are we studying if not the case? Are we studying like a scientist's belief about something, or are we studying the underlying something and then forming a belief? Okay. So I say Clayton wants you to believe the big lie that frequentism is bad for science, which is, I think that's the takeaway from this book that he wants you to think. But if you look at The Lady Tasting Tea by Salsburg, or Creating, I don't know where my copy of Lady Tasting Tea went, but Creating Modern Probability by von Plato, they talk about frequentism tons in science. I already mentioned experimental design. You have sequential analysis. You have quality control. I mean, there's so much stuff. Bootstrap, modern stuff. So, I had in this article, I forget where it was. It was like in, where was it? Chance magazine, maybe, or Statistical. Oh, I'm sorry, Insignificance. Yeah, Insignificance. So there's an article called The Airport Fallacy by Gunter and Tong that in 2017. And I respond, yeah, frequentism is an embarrassment, but it's an embarrassment of riches, because it has done a lot for science. So, if you have some questionable research practices, that's no excuse to throw frequentism out with the bathwater. So, and I just do a quick, to try to answer that, I just do a very quick look at Nobel Prize winners. Now, I'm not saying they don't use Bayesian methods too, but I'm saying at the highest levels of science, like, Nobel Prize winners, they use plenty of statistical tests, p-values, t-tests, f-tests, all over the place. And Laura von Holstein, she proved something pretty cool with one of Darwin's theories of evolution, and she uses some, statistical tests and stuff. So I thought it was like, I don't know, to say it's bad for science. It's used primarily in science, but also other areas. It's kind of the dominant statistical methods. So if you're just going to focus on the misses and forget the hits, I don't think that's a good argument at all. Now there's some articles about scientists and others talking about how important the null hypothesis statistical testing is. So Hagen has one. I suggest you check that out. Adams, an epidemiologist, talks about it, how important they are. Cook and others say there is no competing paradigm that has to date achieved such broad support. Even the more modest proposal of dropping the concept of statistical significance could make things worse. And on the idea of getting rid of frequentist methods, Deborah Mayo writes, misinterpretations and abuses of tests, warned against by the very founders of the tools, shouldn't be the basis for supplanting them with methods unable or less able to assess, control, and alert us to erroneous interpretations of data. And then don't throw the error control baby with the statistics. Don't throw out the error control baby with the bad statistics bathwater. So she wrote this book, Statistical Inference at Severe Testing. It's an extremely good book about probability, logic, philosophy, inference. It has frequentist, Bayes, likelihood. Really good. I highly recommend it. Probably one of the best probability and statistics books easily written in the last couple decades. I have this graph that I really like because it shows frequentist methods over time. Supposedly it's bad for science, but it's used in sciences. So, this is a well-designed scientific experiments and putting confidence intervals on each one. So this looks at estimates and confidence intervals for gamma, the deflection of light around the sun, from just 20 experiments. And you can see that, if the Newtonian kind of version's right, we expect gamma to be around 0. But it looks like most experiments are around 1. Now, I like this because you can see, as we learn from previous experiments, what we don't need any Bayes for, but we can take that background information, and again, we don't need Bayesian priors, but we can use that knowledge, set up better experiments, and you can see the results get tighter around, or at least the estimates get around gamma line more. But it's also important to note, if you take any one of these experiments, you have a piece of something, but you don't know what's really going on. Like if I take this first experiment, I might think gamma's around 1.25. I might think there's a flaw because it's so far away from 0, gamma equals 0. You don't know. And then you get the second experiment and you say, okay, one's way above, one's below. Yeah, maybe it's around 1, but our error bars overlap, So really, kind of science, some things don't happen like right away. They happen over time. And I think this is a great graph to show that, to show that frequentism is good for science. Maybe just be a little patient, design experiments really well, collect your data. And I'm going to stop it for now